I'm very excited to introduce our first keynote speaker today, which is Saman Amarasinghe. So Saman was very keen to come to travel and present his keynote today in person, but due to a family medical emergency, he was unable to travel, so he's going to be presenting his keynote remotely. So Saman is a professor at the Massachusetts Institute of Technology. He leads the Commit Compiler Research Group, and his group is really a world leader in the development of high-performance DSLs. So you may have heard of Halide, DSL for image processing. This was developed out of Saman's group. It's running on probably all of your phones. I don't know how many billions of devices now in the world are running Halide programs, quite amazing. But this is just one of a series of fantastic projects that Saman has done. So there's Streamit for streaming computations, there's Petabricks for algorithmic choice. I mean, it's just incredible. And I did a little bit of research and counting. I hope I got this right, but Saman has published 17 papers at PLDI. The first paper was in PLDI 1993, and this is all the way up and through a distinguished paper here at PLDI 2026. So just an incredible longevity in our community. Saman was named an ACM Fellow in 2009 for contributions to high-performance computing on modern hardware platforms, domain-specific languages, and compilation techniques. And then beyond all that, Saman is also an entrepreneur. Maybe you knew, maybe you didn't, but Saman actually founded the first internet service provider in Sri Lanka. Back when, he founded a company called Determina, around optimization and security that was acquired by VMware, and he's still very involved in entrepreneurship activities to this day. And then finally, on a personal note, what got me here, what sparked my interest in programming languages? Well, it was a really fantastic compilers class that I took in the fall of 1999 that was co-taught by Saman and Martin Renard, really inspiring, so very big reason why I'm here today. So let's give a warm welcome to Saman for his talk.
Thank you so much for that amazing introduction. I guess probably my biggest achievement is probably getting Manu interested in compilers. So thank you, Manu, for both introduction and basically inviting me to give this keynote. So today I'm going to talk to you about programming language design and implementation in the era of machine learning. Little bit of a pun in our conference title. Three topics I'm going to talk about. And first one is basically lessons from the past. We have been doing a lot of stuff with machine learning for a long time, and I want to bring that up to show what can happen in the future. So if you look at normal compiler, this is what you look at. But in a machine learning, you have to look at a much bigger view. For example, somebody take the language manual and can write the front end, again, can write the back end. Also, somebody look at something like a Dragon book and write all the optimization. All these things can get impacted by machine learning. So what can be the future of compilers in the way of machine learning? I think there could be three possible futures for that, or three possible things that can happen. One is there are things that the current compilers are having a really hard time doing. Machine learning can augment a traditional compiler and help a compiler achieve a bunch of things it can do today, it cannot do today. Second, more interesting, a little bit scary, is writing compilers are hard and a very time-consuming thing, and sometimes compilers are way behind the architectures that it's trying to compile for. And machine learning can be used to generate traditional compilers. And most scary of them all, machine learning can be used to replace traditional compilers, and you don't even need a compiler at all and achieve what compilers do today completely with machine learning. So let's look at all these three. So if you look at machine learning augmenting the traditional compilers, that is not new. In fact, in this part, we built something called Meta Optimization 2003, which was the first compiler to internally use machine learning. Let me tell you a little bit about that. So one thing we realized was a lot of times in compilers, you have to make decisions, but in the what you call priority functions. And the decisions is the Achilles heel of the compiler, because most of the time they're so far early that you don't know the impact, but the decisions you make will have a performance impact in here. And there are priority functions all over compilers in there that compiler writers come up with these very crazy heuristics to choose. And the nice thing about that, all the priority functions are legal. You can come up with any set of choices. Only thing will be programs will be much slower if you don't find the right priority function. So what we did was use at that time the state of the art, which is genetic programming. The idea there is you look at a priority function, you look at a bunch of inputs that should dictate the priority function and start generating a random functions, a bunch of random functions, and slowly evolve that by looking at the performance in bunch of programs you can get. To our surprise, by the way, this time machine learning is not a hot topic. Nobody believed in it, and especially systems people. What we found was things like high the condition. Should they leave the condition and basically take the cost of branch mispredictions, or have both sides going and take the cost of extra execution? And this is very complicated decision making. And what we found was we can actually get about a 25% increase in general programs, and the things that we are trained on, almost a 50% increase in here. We hope we learned something out of it, but we didn't. It created some crazy function with bunch of different measurements to make that decision. It was not that enlightening. Today, nobody trying to look inside machine learning to learn, but those days we were hoping to gain something, but we didn't. But that was a very interesting thing to show us that the compiler engineers, we think we are very smart, we can come up with heuristics, but the data-driven techniques can actually sometimes be better. The next thing we looked at a few years later is vectorization. The idea there is, can you completely build a vectorizer using machine learning? So no human intervention at all, just complete use machine learning to build a vectorizer in here. And vectorizers are hard. So let's see whether we can do that. So one possibility would be you get your source language, put it into a bunch of tokens and feed into some kind of machine learning pipeline, and can you get the basic nice vectorized code in here? This is a nice thinking, but the problem is machine learning do not guarantee correctness. And unfortunately, in the soft compiler community, we have trained everybody to expect perfect guaranteed output out of our compilers. So unlike NLP, these don't work very well. So this is a time where we were looking at systems like AlphaGo. The nice thing about AlphaGo is the board produced bunch of usable heuristics in here, bunch of usable moves. Then your choice is to basically find the right move in there. And if you get all the right moves, you win, otherwise you lose. So can you use this in our compiler in here? So what you can do is you look at the program in here, figure out what are all the valid small vectorization possibilities in here. What are the things you can combine together in something like supervised level parallelism? And then choose one and implement that. And that gives you a new configuration, new state. And then basically iterate through that, find the next new possibilities and iterate through that. And at the end of the day, the reward is how the speed of execution. So can we do that? But to do that, we need to train this system in something like a Markov decision process. How do you train it? To our luck, just before that, we built a system called GoSLP. GoSLP was a very interesting system because what we did was we used integer linear programming to find the optimal schedule. This is great, we get optimal schedule, but the problem with integer linear programming is if the program gets a little bit too big, it just doesn't work. It just run infinitely or run out of memory. So this is really nice for small programs, but didn't work. But since it's optimal, we could use it just to train a system that to do the selection using Markov chains. So this is the performance of GoSLP over LLVM for a bunch of benchmarks. And to our surprise, just by using this imitation learning, we were able to build this Vimal system that is really, really good performance. In fact, in many places, Vimal was better than its teacher, than GoSLP. This is kind of a little bit strange, you might start thinking. And in fact, in few places, LLM is even better than GoSLP. So now you might have a question. How can anybody be better than Optimal? Isn't Optimal the fastest, best? And this was a big interesting problem. But the interesting issue here is when you look at Optimal, Optimal is again some type of a cost model. And because we are doing a linear cost model for integer linear programming, our cost model was way not accurate compared to the actual cost of running the program using out of order superscalar machine. And what I'm showing in this graph is the LLVM SLP optimization. So each loopness, some stuff it did about 60% reduction, some stuff not that much. Here's what LLVM and GoSLP for most cases is better. But there are certain things it's worse because GoSLP's cost model thinks it's doing better, but the actual cost was not good. So this is a place where we realize cost models have a big impact in performance and our cost models are not good. We also realize state-of-the-art cost models were also pretty bad. So things like LLVM, MCA, and Intel IACA cost models basically predict the execution time on modern hardware. They have about 20% error rate. The issue here is you have a basic block. Assume there's no branches or mispredictions, very simple execution basic block. You feed it to this entire beast of an Intel machine and it produces number of cycles. There's so many things going on in this processor that you have to simulate to get that one. Worse, Intel doesn't even tell you how some of the internal things work. So how do you even get that? So what you do is Intel has produced like huge thick manuals describing the performance of each instructions. And you have to look at that and write your own basically specifications of the cost of instruction. This is not easy because some instructions, in fact, if you look at the instruction, one instruction manual says normal execution time in here. Completely different book says if the inputs are zeros, there's a bypass that can you run much faster. And you have to look at all these books to produce the cost for that instruction. So instead of going through this thing and suffering that a lot of compile engineers do, can we actually train a model in here? This is where we came and developed itamal system. So what itamal did was basically said, get that basic block, feed it into a LLM, not LLM, just a simple LSTM at that time, and get it to predict the runtime. So you have a database base of what 1.4 million basic blocks we collected. Ground truth is very easy. Run it and measure it in that architecture. And then you run it through a neural network and then basically backpropagate any errors to basically train the neural network. And what we found was by doing that, we could come up with a cost model, but 2 times more accurate than anything out there. And this was really cool, and we can use that. In fact, Charit Mendis, who did this work, then went on to build something similar in XLA architecture and build a cost model to make many decisions in XLA, realize using that cost models can have a huge impact in the performance of some of the kernels they were able to compile out of that. And also, as XLA architectures keep changing and the new TPU comes about, architectures for XLA keep changing, new TPUs come about, instead of spending months and months coming up with a cost model, within few days you can retrain it and you have a really valid cost model for that new architecture. So this is a really cool way of dealing with architectural changes and impacting the compiler faster. Next, I want to look at how to use machine learning to generate traditional compilers. Okay, so not just modify the compiler, completely generate a compiler. So in there, I want to look at 2 projects. One is this vegan project of generating the vectorizer completely. So we were doing a project of trying to build a vectorizer. And I told my student, why don't we build a true vector writer for Intel x86 architecture that has AVX extensions? He was not that happy because AVX has SSC, AVX, AVX 512, all these things had multiple thousand instructions, and he didn't want to spend all his time trying to cut each instruction and code it in the compiler. Normally, this is probably multiple engineers, long time project. But he came up with a very clever idea. Intel published a very detailed architecture manual that talks about each instruction, what it does, and even a little bit about its performance. Can we use the architecture manual to directly generate the compiler? So that's what we did. Using the architecture manual, we generate the compiler for that architecture. Then, if you give a sequential program, it will vectorize the program for that architecture. Nice thing about that is, minute you have a new architecture, sometimes if you look at something like production compilers, something like LLVM, certain new instruction took more than 10 years for LLVM to generate a reasonable code for that instruction. We, on the other hand, in a couple of hours can do that. So here's some interesting results out of a very important kernel out of the TVM program. Doing a matrix vector multiplication. If you look at carefully, the loops are running for fixed number of iterations. So ICC compiler says, this is great, I know what to do. I unroll everything and created this huge program. But ICC don't have a superword level vectorizer, so it couldn't do anything for that. It just ran this sequentially. GCC did better. It was able to do some vectorization and good performance. Clang, on the other hand, did a really good job, did a lot of vectorization, get about 2.2x performance in here. Then we fed it to the vegan. It produced the entire code in 4 instructions. So you'll ask, how much magic is vegan? There's not much magic in here because Intel has introduced these dot product instructions a few years ago. And Clang LLVM still doesn't have that inside its compiler, so it doesn't produce that. It's using other instructions, older instructions to do that code. On the other hand, we were able to get all the new instructions, and the dot product instructions is a clear fit, and we directly generated that and got really good performance. So going forward, when architectures, accelerators change very fast, and compilers are struggling to keep up, I think having this ability to automatically generate backends will have a big impact in here. The next project I want to talk about is from Professor Martin Reinhardt. So normal traditional compiler take the original program and compile that. The interesting thing about traditional compilers is we just have to trust it. You run a bunch of tests and you say this compiler works, but there's no guarantee. On the other hand, something like a credible compiler says you take the original program, when you compile it, you not only produce the compiled program, but you produce a proof that the optimized program has the exact same behavior as the original program. And you can use a proof paper to validate that. If it is valid, I accept it, otherwise it's not. This is a very great concept, but as you know, it's very hard to write things like that, generate proofs and in a general purpose way in a compiler. So this has been a kind of an interesting research project. You see a lot of papers in PLDI, but never a practical thing because it's really hard to do. So what Martin did was, he was in sabbatical in Singapore. He said, I am going to write a compiler like that. So what this compiler does is, only thing that's unverified is the parser that takes the input program, which is a subset of Fortran, and produce a pretty printer that's basically ARM assembly. Those things are not proven. Everything inside the compiler is either that pass is proven or it will generate a proof that the transformation it's doing is in fact accurate, and you can check that proof before you accept the output in here. The neat thing about this is he wrote almost 40,000 lines of code by himself in 34 days in here. As you know, senior faculty are not the best programmers. I mean, we have, I think, very rusty when you get programs. But Martin did it by himself. And the interesting thing is, he said he never looked at a single line of code. Only thing he looked at was the conversations he had with Claude and the proofs. Those are the only thing he looked at, and he produced this compiler in here. The interesting thing in here is when we are using these systems like Claude, people always complain about AI slop and things like hallucination and how hard it's difficult to trust that. Here, we have no idea how complicated and unwild the code is that produced, but it also produces a proof that the code is correct. So at the end of the day, you have a compiler that is not only producing code, but come up with a correctness proof. So why do you need to know what's inside if it is there's a proof? So this is a very interesting thing that's going forward, and both the kind of using proofs and also what a single, not probably that great of a programmer or rusty programmer can do using these new tools. So can ML replace a traditional compiler? This is the most scary part for me as a compiler writer. So there are already companies trying to do this, generating kernels with no compiler technology whatsoever. But I think compiler technology here can also help. We know a lot about the programs, programming languages. We know about all the optimization. We know a lot about the architecture specifications. So can we create agents that LLM can basically ask for information and get advice when it's generating code? The interesting thing about when LLM generate code is you have no guarantees whether the code is correct. So you need to also do some work to enforce the correctness in here. So if you look at this, what you can do, there are two things. Compilers, everybody expects compilers to be correct 100% of the time. But today, what we do is basically we test them. There's not guaranteed in there. We have a lot of good tests and we validate in there. And we can use LLMs to both create the program and also create a test set for that program and run it, validate it, and get a proof of correctness in here. Not a proof, but a validation of the program is correct. But more excitingly, we had never written proofs because programmers hate to write proof, at least outside this community. But with LLM, we can also get it to write proofs, as Martin's system showed, that then we can verify either entire compiler or each program is correct, and then we can actually use LLMs to do things that probably even better than today's compilers in the realm of correctness. So there are a lot of interesting opportunities there, so this can be exciting. So next, I'm going to go a little bit broader and also looking at a bunch of new ideas for the future. So if you look at what has been going on for a long time, programming workflow haven't changed. Basically, humans wrote programs from the time of Fortran, and a compiler will take that human written program and generate assembly. That's what we did. But machine learning is completely upending that workflow. Now people are writing in English, and the English is what fed into LLM that creates the program, and that's been run in here. And there's all these things was ML for programming languages. So there's a lot of advantages of vibe coding. For its speed, oops, and sorry about that. Speed. Basically, you have seen people that can generate thousands of lines of code per day. In fact, we look at some of the repositories that are public in there, and with their contributors normally used to do about 100 to few hundred lines of code a day. Now they are submitting tens of thousands of lines of code a day because they're all vibe coding in here. If you can describe it, these systems might be able to build it. So it's amazing what you can do in here. I have done things that using vibe coding that I have no clue what I am doing. They find interesting libraries that I didn't know that existed that solves those problems and use them and produce correct programs. The breadth is amazing. There's no ramp up time for me to learn for weeks what these things are doing. And even the boilerplate code, I don't have to write those things. It all can generate it very nicely in here. Now the question is, do you even need a compiler? Can we basically take a program, English in there, directly go to assembly language, completely get rid of a programming language? And again, companies like Standard Kernel is doing it. And there are many people who are saying this is the future. They say the English is the programming language, programming will be obsolete. This is scary. Is programming language dead? And besides this kind of societal level impact we have had in programming languages, where every programmer used one and every device actually has artifact generated by one, will programming languages become a niche field? Which is kind of a scary place to be, scary thing to think about where our communities will go. I don't think so. So my argument is, from the time we introduced programming languages, there was a reason for doing that. Because English has a lot of problems compared to programming languages. First of all, programming languages' main cases are unambiguous. English is very ambiguous in here. Programming languages are machine checkable. It's hard to do that with English in here. Programming languages are nicely composable. You have nice interfaces that can be put together. If you try to compose in English, you need some lawyers writing huge big documents to make sure that things will compose together. That doesn't work in programming in here. We can guarantee that same program given same input produce the same result, very reproducible output. You can't say that for English. There's a lot of ambiguity in there, a lot of way to reinterpret this thing in here. That's a problem in here. And in many cases, for very precise thing, programming languages are a lot more concise than English. It can flip in some cases, but this is interesting in there. So there are advantages. But that said, LLMs are really changing the landscape of programming languages. LLMs are bringing a lot of new capabilities. First of all, you can go from English spec to code. So that's a very interesting capability. Other thing is the context window of the LLM is in the millions of words, whereas humans, you can remember what 20 words. The entire designs of programming languages were created for the human context window, for humans to deal with that. And there are capabilities like decompilation that I'll talk about a little bit later. So that means LLMs are bringing a lot of also new opportunities. For example, tokens are a lot more expensive than process cycles because every token is many matrix multiplies and a lot more electricity than that we can do in programs. So we have opportunity to optimize for compile time in here. And again, English has a lot of shortcomings as programming languages. So I have been thinking a little bit and say, what kind of things as a community we can do to help this new world? So I'm going to talk about three things that are just ideas in my mind. The interesting thing is, this is a great idea today, but in 3 months, when the next generation of Claude shows up, all these things might be obsolete. So take it with a little bit of grain of salt, whether you want to go jump into things like that, because it's moving very fast. So let me talk about these ideas. First idea is LLM oriented IR. Today, LLMs are generating programs for languages written for humans. Those languages were developed for humans, that optimizing the human capabilities. But we need new languages that LLMs can generate that are optimized for LLMs, not for humans. So there's some current work in here, but mainly about syntax level optimization. For example, why do you need very complex names that had hundreds of words? You can have one token for that. Things like a lot of language keywords, you can have a specialized token, so you can reduce token counts by doing things like that people have looked at. But I think you can do better. So one thing you can look at is language that has, of course, used to have a lot of this language has been expressive. You need to write every possible thing with this language that you are going to generate in here. We need to be precise because that language is feeding into a compiler. So you need to say something precise in here, not like English. The most interesting thing is it has to be compiler complementary. Things compiler are good at, we don't have to do, but things compilers are bad at, we should get this language, the LLM do that into this language. And of course, you want to do it in a token economy way in here. That's what we want to do in here. Something interesting is now when you write LLM generate something like Python or C, you as a human can go and look at and debug it. Now this language is not going to be human readable. Then you need to have tools to go and examine what LLM does if there's bugs in here. So that's a requirement in here. So if you look at something like C and Python as a language LLM generated versus ideal language, both has to be expressive, both has to be have high precision. Right now, C and Fortran or Python doesn't think at all about LLMs in that they are created for humans, whereas this one can optimize for LLMs. And again, really optimize for tokens in here because as you know, tokens are getting very, very expensive. One issue that you had to probably deal with is able to humans to understand that. C and Python we can go and read, even though it might be sloppy and huge number of lines of code, still we can read. This ideal LMIR would not be easily readable in here. So we need tools for doing that. So here's another thing I thought about. If you look at how we write programs today, there's a part of program that I call source of record. People call it source of truth, reproducible things, provenance, all those names in there. What that means is that is what, in essence, you are going to check into GitHub. That is what that somebody else can clone that GitHub repository, run it to the same tool chain, and produce the same executable, same semantics in here. Everything else is generated, that doesn't matter. So there are a bunch of properties you want in this language of recording. Again, it has to be expressive. It has to be precise in here because we have to unambiguously tell what you can, what you want to do in here. Whereas the tool should not do a bunch of guesswork to do that. It had to be able to read, update, modify, because that is the level you are going to maintain a very large project. In here, modify, update, add, all those things are possible in that level in here. Again, it has to be reproduced. If you give that record to toolchain, you should get exact same results in here. And again, you should be able to evolve that thing. So that means a lot of things like modulability, refactoring, local reasoning is necessary. All the things we learn in software engineering is necessary because this is how we build large projects that last for a long time. And we should be able to also specify things beyond this semantics like performance, security, even able to verify what this is correctness. We should be able to do all those things. So that is important property of this language of record. Right now, previously we used C and Python for language record. Right now we are using prompts and code. And both are expressive, but prompts and code, it's very not clear semantics because prompts might be saying one thing, the generated code might do something different. Both might not be human readably good because again, C language can be much more longer than a very simple English sentence. On the other hand, prompts might be succinct, but you have also the code going on in there. Having both prompts and code and English and code doing the same thing can be confusing. And evolving become much harder because what are going to change? If you change the code, prompts become obsolete, vice versa. So there's an issue, even though we have set to these prompts and code, they are not the best way to build a large project. And here, as a community, I think we can contribute to that. What we want is develop the right way to do a source of record in here. So English can capture specification, but we need something else to capture other parts that we do in a programming language at a very high level. What components to use, what APIs to use, data structures and control structures, synchronization and parallelism. Can we capture those concepts in a much more higher level programmatic way on top of the English specification in here. And this is a little bit similar to algorithm languages in a scheduled language pair in something like Halide, but in a much more broader way we can do it here. And if you can do it really well, we don't even need have a code recording in there. So when you GitHub, we can only have your English and this source of record language, and the code can be generated again and again in a deterministic way. If you can get there, the world would be much nicer in here. So if you look at this thing, if you can build a language like that, we can get best of all the worlds in here, except probably evolvability, because now you again have English and this that has to coexist in here. So there's a lot of interesting things you can do as programming languages in this new domain in here. Another interesting thing that I find is the toolchain path in here. Right now we have one-way toolchains. What that means is you write with high level, like something like C, and generate everything down. And the source of record is that high level thing. That's what you put it into GitHub. But now assume you want to change something low level that you can't write it in C. You want to do some kind of assembly hack or some optimization low level. You do that. And now it becomes part of the source of record too, because it has to be reproducible in here. Worse, now the original source that first generated that part is now stale. It becomes out of date in here. The problem with this thing is now that can't be source of record, and if you are trying to do any kind of update, evolution becomes very tricky, because you have to both do at high level and low level, both has to evolve together. The interfaces have to keep evolving together. This becomes a much harder thing to deal with that. So what comes to the rescue? These LLMs are getting good at compiling both directions. Things like, Mythos didn't even get released. The US government banned it because you can take the assembly and generate something almost a program level that you can understand the program semantics. So you can go bi-direction in here. So what that means is at every level, if you change that, you can go to the higher level and update that level so you can maintain the consistency. This even gives us an opportunity to have multiple levels of record in here. You don't want to have a single level, you can have multiple levels of record, modify any level, and use the LLM to make sure that it propagates both downwards and upwards and get everything updated and consistent in here. This can probably give some very interesting ways of building large systems that I think as a community we should explore and look at in here. What we have done so far is evolve the existing workflow in here. Current workflow is basically easy because there's a minimal disruption to existing workflows with LLMs. Humans are familiar with languages like LLMs generating. Models are familiar because models are trained with millions of lines of existing human written code. So this is where we are, even though now LLMs are doing that. But I think there's an opportunity to completely redesign these workflows, languages, and compilers, and see what's going on in here. A ground of opportunity. But before going that, it's not that simple. Finding the most impactful, useful programming language is not a science. What's the best for programmers versus best for LLMs? You can basically say, if you get a bunch of tasks, least line of codes needed to write or least amount of time to write that thing correctly is for humans the best. Probably the least number of tokens used is the best for LLMs. You can have this kind of measurement to figure out your language is good. But that's not that simple. For example, if you look at humans, you can do this measurement by teaching this language to undergrad for half a day and get them some test in here. But that doesn't mean that some good programmers using this for a week for a project and then using the test might be doing much better. Even better, you get expert programmers who are fluent and experienced in the language. They might have a much better, faster, easier way of solving problems. So there's a lot of complexity. That's not that easy to test to. That's why as a community, we probably don't test that much of a language, whether language is a good language or not. Same thing happened with LLMs too. You can use the language manual and some example as a rag and measure whether that language is good. Or you can fine tune a LLM with thousands of lines of code. Or if you are a foundation model generator, you can train the LLM with millions of lines of code and figure out doing that. So again, there's a complexity in here that makes it probably hard for something like a universities to really experiment in there, because we don't have the millions of dollars to chain a large language model with these new languages and see how good they become. But I think there's a lot of opportunity to do here. So both LLMs and programs are trained in these current languages. So that's how we are in, I think, basically suboptimal, like a local minima. But I think there's some interesting work that can be done to find the optimal languages for this new world in here. Okay, for last few minutes, I want to have a little bit of plea for the PLDI community. There's nothing technical in here. Hopefully, you can shout at me for what I'm saying, but I hope some people will take it in heart and do something with it. If you look at today, GPUs are having a global impact. So, in 10 years, the non-trivial amount of US electricity, entire US electricity will be used by these data centers. And if you look at inside a data center, more than half are used by GPUs. So what that means is about $83 billion is used by GPUs in 10 years in here. If you can reduce the stalls, if you look at the huge percentages right now, stalls, if you reduce the stalls and make the code 10% faster, that's a $31 billion of savings. Huge. And who can do this? So I looked at the kind of spectrum of programs. In one extreme, programs are very dynamic, huge number of lines of code. Other extreme, small code, static. And this dynamic codes, basically, it's not a compiler's job. It's like operating system, database, networks people doing that. If it is very simple, it's assembly hacking, performance engineering, or even building custom basics. Middle is our sweet point in here. Probably scheduling language can extend a little bit to the left, but that's where we are. The old school application, things like application servers, web servers, were completely in the domain of databases and networks and people like that. When machine learning started, they were basically assembly hack, things like flag session and pre-training in here. As we move into post-training, fine-tuning as complex inference, they are becoming compiler problems because programs are large enough. There are some dynamism, it's not completely static, that we need compilers in here. And in fact, compiler community has a big role to play here. If you look at what's out there, there's a huge community, billions of dollars invested in new startups. The experts are getting paid in millions of dollars doing this thing. There's a huge amount of work happening in here. So the interesting thing is when things like this happen in industry, who are the predecessors in research that led to this? Who are the basically gatekeepers and drivers of that led to this? I looked at bunch of papers that are talking about these techniques that becoming out there. I look at from the Google Scholar citations number, and yes, there are a lot of papers that are basically led to some of these projects in here. And they have really good citations too. If you actually compare it with PLDI, the highest cited paper, these actually more cited papers in here. But the interesting thing is, only one of those papers were published in PLDI. It looks like a lot of those papers, three of them are in fact published in OSDI. That distresses me a little bit. And then I start talking to some of these authors. To my horror, realize at least two of these things were PLDI rejects. They submitted to PLDI, PLDI got rejected, reject this paper, and now they're in these other conferences in here. So I talked to some of these authors a little bit and trying to figure out what are we doing. So why are they not in the PLDI? We might think as a community, we don't need them. We don't need these people in here. There are a lot of interesting things that I thought that our community says we don't need them. These are just engineering papers. We are a community who talks about a lot more deep science. We don't need them. Or I can even relate this. A lot of these things happening today, we did it in 90s. There's nothing new. So it's not PLDI worthy. That's what I think some of our community can think. Even me can think a little bit like that. But then if I talk to the people who's in this world working on these things, they said some damning things in here. Some person said PLD is becoming less relevant over time. It's more of a Popple-like conference than a less than Asplus-like conference. Or PLDI tends to be strong viewed, fit their mold. It's creating a little bit of echo chamber from other communities. Or PLDI has historically been less welcoming to interdisciplinary work than other CS community. These things hurt. So my plea to PLDI steering committee, next generation PCs, chairs and reviewers are ML compiler should not belong into OSDI. It should be PLDI. We have to do something to make sure that this line of work get into our community and we become the people who lead this work in here. And some of this criticism I think is valid and we need to figure out how to help in that. And PLDI, in my opinion, in one of the best and highest respected conferences ever. And this was like that when I started. Our predecessors did a lot of good work to bring PLDI to that stature, and it's up to us to keep that gradient in here. So there's a lot of work for us to do. After that rant, let me give you a couple of final thoughts in here. When I was a graduate student in the 90s at Stanford, the commercial programming compiler was GCC. And I also talked to a lot of natural language processing people because the internals of compilers were very similar to NLP there. Something interesting happened around 2015. The natural language people completely dropped everything they were doing and completely switched into using machine learning techniques in here. Lot of things that were bread and butter just became completely obsolete in there. I believe we as in a compiler programming languages community, we are facing this. In next 5 years, programming tools will look nothing like what's today. So we have a choice to make. It's very rare to get an opportunity to completely redesign the entire system. The programming tools will be completely redesigned and we get that opportunity to completely redesign what this tool chain will look like. I think this is amazing. I think we should take that opportunity. If we don't do that, our work will become obsolete and we will just basically work towards sunset. So I think we have a choice. I think a very exciting choice. And I hope we as a community will embrace that and move forward. With that, let me stop. I'm sorry I went late and open up for questions if there are any time.
Okay, thank you so much, Saman. I think after that ending, we have to make time for at least one or two questions or points of discussion here. If anyone has them, they can walk up to the mic.